Today is the third and final lecture in this wonderful series from Rohit Pappu, who I think all of you know by now. Rohit really is one of the pioneers in the field of molecular condensates, and his lectures are part of this larger kitchen table talks series in which we're inviting prominent researchers in the field of condensate research to share their thinking, to help the whole community to go a little bit faster by learning together. And all of these lectures are on the website condensates.com, so you can look for them there. In the last two lectures, Rohit walked through the basics of molecular grammar, the stickers and spacers model, phase transitions of IDRs, intrinsically disordered regions and proteins. And now this lecture will cover phase transitions in multi-component systems, as Rohit would say, trying to make this more real, looking at real world situations in which phase separation is occurring. And Rohit, as I'm sure many of you know, is the Edwin H. Murdy Professor of Engineering and the Director of the Center for Science and Engineering of Living Systems at WashU in St. Louis, has been a key player in the condensate field since its beginning. Last week, I shared a little bit of information about Rohit that was given to me by several people, that Rohit is an excellent dancer and has been known to lead dancing sessions at Gordon conferences. I have since then learned that he is also an avid fan of cricket. And so if you have questions about that, you could also check with Rohit, and he'd, I'm sure, be happy to answer those questions, as well as any you might have about condensates. So Rohit, the floor is yours.
Thank you, Mark. Setting dancing and cricket aside, so we'll jump in today to discuss the phase transitions in multi-component systems. And this sort of builds on the foundations that we've set forth in the first two lectures. So the program for today is to first talk about protein-RNA interactions and phase transitions, because as many of you will acknowledge, RNA is a key component of sort of many of these condensates. And so, you know, an RNA is just not some random polymer. We have to think a bit harder about the specifics that RNA brings to these condensates. I will then segue to thinking about or articulating ways to think about ligand effects on phase separation for multivalent macromolecules. And then basically point the way forward for the way we've been thinking about complexities of multi-component phase diagrams and what the broader implications are going to be. So let's start with our stickers and spacers model. How might this be applied to describe the phase behavior of RNA molecules with their protein counterparts? And so to keep life simple, understandable, and potentially relevant, we'll focus on dipeptide repeats, which many of you are aware of as being quite important in the context of C9orf72 repeat expansion disorders, and particularly in the context of ALS, where seemingly toxic dipeptide repeats are generated by these repeat expansions, and they interact in ways that they're not supposed to with RNA. So this work that I will tell you about today is primarily driven by Stephen Boynems, who at the time, basically, this is science at its very best, the way I look at it. Stephen had sort of moved from Belgium to Stanford. He'd befriended Alex over the years, and they developed a very strong connection. And then one day over coffee, Alex started telling me about all these interesting things that were going on. And of course, as any PI would, immediately I sort of set everything aside and decided to spend all my time at Alex's desk, virtually speaking, of course. So the system of interest that we'll focus in on is a proline-arginine repeat. This is a dipeptide repeat system. There are GR repeats. There are other repeats, SR repeats in the nuclear speckle, which we've also focused on quite a bit recently. But let's just simply ask the following question. If we were to take a model polycation, and we start to think about different homopolymeric RNAs, which actually turns out to be a reasonable way to conceptualize what might happen when we think about naked unfolded RNA molecules coming off polysomes, what might be the phase behavior. So these are sort of experiments done at sort of roughly 1-to-1 ratios of PR30 with different homopolymeric RNAs. And the observation that jumped out was that under these conditions at concentrations, joint concentrations of modules that are sort of in the low micromolar, one starts to see these fairly well-defined spherical puncta. Here it's the PR30 molecule that is being labeled. But interestingly enough, when one has a polyguanine, essentially what one starts to see are these fairly irregular morphologies. And those of you who know your nucleic acid biophysics will appreciate that it is reasonably well established that G tracts will make G quadruplexes. And so one hypothesis that started to take root was the idea that RNA structure, and this is not so terribly new because Amy Gladfelter has actually led the charge on this thinking, that RNA structure might actually have a contributing role to dictating the morphology of condensates. What was particularly a fun project to work on was Venera Weinhardt's work at the Lawrence Livermore National Laboratory using soft X-ray tomography, where you can actually use sort of anomalous scattering properties of water as a way to sort of image and construct tomograms, and you can actually see these spherical condensates for, you know, the adenine, uracil, and cytosine, but you start to see these very irregular morphologies for the guanine-rich systems. So the one question that emerges is clearly there is a sort of impact of RNA structure on condensate morphology, and that was sort of based on the sort of connections to ideas in the literature that G tracts make quadruplexes. But you can control RNA structure in a much more defined way. And the way to do that was to basically incubate PR30 with mixtures of non-base pairing RNA molecules, again, homopolymers. And you can have, you know, AC combinations or UC combinations. They don't form canonical Watson-Crick base pairs. And basically what you start to see, again, here PR30 is the entity that is labeled, and you see basically the maintenance of the spherical morphologies. But then when we switch to base pairing RNAs, depending on the ratio of the structure forming entities. So at the limit where you have purely homopolymeric systems, you see essentially purely spherical morphologies. But as we transition through these base pairing mixtures, you start to see much more irregular morphologies. I'm sure at this juncture you're asking lots of questions in your head about, you know, dynamics, etc. We're coming right to that. So the question on the table for us was, do these structured RNAs, or the ability of RNA to engage in structure formation, does that lead to the formation of solids, or is what we're observing something metastable and dynamically arrested? So for that, we essentially turned to simulations. I introduced PIMS in the last lecture, developed by Alex Holhouse, who was then a postdoc in the lab. And so essentially what Alex did was he, you know, developed PIMS to be able to do simulations of protein RNA mixtures. And the type of simulation that, you know, one would sort of readily observe based on sort of typical types of interactions for PR30 and poly-RA is the formation of these spherical condensates. They become a little sort of hard to fuse past a certain length scale, but that's largely sort of a move set issue. But then when you look at mixtures of PR30 with poly-A and poly-U, you start to see these sort of dynamical arrest. But then what Alex had was the thought that, hey, maybe these things are sort of locked in or trapped. I'll give it a thermal kick and then essentially set in an annealing protocol. And indeed, what you start to see is the formation of, you know, fairly well-defined spherical condensates. So the picture that emerged was, for lack of a better term, this dual funnel model, where if we now project the multidimensional free energy diagram free energy surface rather onto one coordinate, effectively here by conformation, we really mean morphology of the condensate. You effectively have a metastable trap, so to speak, that can basically be overcome by a sort of thermal kick and an annealing process. Now, for those of you who might think that this is something brand new, let me disabuse you of that, because in fact, dating now back to 1993, Francesco Ciartino, then a graduate student in Gene Stanley's lab, postulated this model for gelation as a way of dynamically arresting phase separation. So here the idea would be that the formation of crosslinks, be they stacks or hydrogen bonds, but the fact that essentially we are perhaps to the right of the percolation line as far as RNA structure is concerned, leads to this networking phenomenon that can essentially lead to dynamically arrested condensates, which will not necessarily be the equilibrium scenario, at least for this particular case. And Stephen then went on to basically test Alex's predictions by taking this mixture and effectively heating it and then slowly cooling back down. And effectively the slow cooling allowed for the reformation of spherical morphologies, essentially leading to the idea that these were actually more dynamically arrested states rather than an equilibrium solid phase. So the other thing that we introduced in the second lecture was the concept of specificity in the form of different types of stickers wanting to make different types of crosslinks. Does that concept of sticker grammar transfer over into thinking about the nucleic acids? So here, of course, we've got a choice of the nucleobase and, of course, the amino acid, namely the cation. And so these are experiments that Stephen did, which are the microreology experiments where you're basically quantifying the fusion of condensates. And the inverse capillary velocity is such that the higher the value, the more slowly these condensates will fuse. And in fact, what you see is a very interesting distinction between purines, the double ring systems, versus the pyrimidines emerging, whereby the purines, which of course now have a higher intrinsic valence, basically ends up sort of retarding the fusion dynamics. And so that was sort of one conclusion. The second conclusion or the second test was to ask, well, okay, if we keep the nucleobase fixed and we now change the cation type, what sort of fusion dynamics might we observe? And again, you start to see this very interesting distinction, and these are, essentially on log scales. The inverse capillary velocity with arginine now, which, as I pointed out in the last lecture, has this delocalized electron cloud, is considerably less like a point charge. And so from the vantage point of its sort of intrinsic quadrupole moment, will allow for more interactions, if you will, and hence more cross-linking per sticker. And you essentially see that manifest here, where when you substitute the arginine with the lysine, the inverse capillary velocity drops, implying more efficient and rapid fusion of condensates. That trend line, so the relative trend line, is preserved as we switch from purines to pyrimidines, and you notice this. And so basically the idea then is that the anion type matters in the form of, is it a purine or is it a pyrimidine? The tractedness matters, is it a G-tract versus not? And also the cation type matters, is it an arginine versus a lysine? What's good for the fusion dynamics of condensates is also good for the internal dynamics of molecules inside of these condensates. And so here what one is doing is basically fluorescently labeling the PR30 and basically watching the recovery upon photobleaching of the PR30 in the context of these different condensates. And if you do the exact same experiment with the PK system, so where the arginine is substituted with the lysine, the recovery is sort of mostly complete and also essentially shows an insensitivity to the purine type or to the nucleobase type. So the last thing that sort of came to us was to ask these questions about spatially organized condensates, because we touched upon this in the first lecture, and those of you who have seen images of protein RNA granules will of course recognize that these are not just bags of molecules, right? There's always a spatial organization to these condensates, and the question is, was that evident in these fairly simple systems? And the answer was actually yes. So here the fluorophore is on the PR30, and you can actually see that there's sort of a core and a shell type of architecture that was manifest. One can sort of get at this again using soft X-ray tomography, and you can again see the electron density is indicative of the fact that there is a core shell architecture, which led Alex to then go back and ask the question of what would be the sort of simplest model that will lead us to a core shell architecture. So here we've got the polycation is modeled as being repulsive for itself. The purine is modeled as having a stronger interaction with the polycation. The pyrimidine, in this case the cytosine tract, has a weaker interaction. And then basically there are RNA-RNA interactions that are of modest affinity, and I should point you to these scales, and these are not gigantic interaction strengths, right? And basically what emerges pretty much spontaneously is a poly-A core, essentially dressed by a poly-C shell. And that just gets completely abrogated if we were to argue that the cation-anion interactions don't show any specificity as far as the nucleobase is concerned, and basically now you don't get any delineation of a core versus a shell. So basically what emerges from this is that there appear to be clear rules that dictate the driving forces for local complexity domains interacting with RNAs and driving condensate formation, what might dictate their morphologies. And hopefully what I've tried to persuade you here is of the idea that if you see something irregular, if you see something aspherical, it does not have to mean that it is purely a solid phase. It turns out that RNA structure, purine versus pyrimidine content, and their patterning will also contribute, as does the valence of arginine versus lysine. And there's in fact a very interesting story about sort of the molecular grammar that distinguishes IDRs that go into speckles, which basically have very few lysines, versus, let's say, IDRs that make up euchromatin or heterochromatin, so in the histones where you seldom see arginines, and conversely in the nucleolus, depending on the state of the nucleolus, there is a very interesting interplay between arginine versus lysine richness. So in ongoing work, what we've actually been doing is working very closely with Amy Gladfelter to now ask how these simple rules actually contribute to the organization and dynamics of a variety of really interesting and sophisticated RNP granules. I urge you to stay tuned. But what I will do next is sort of switch to the topic of essentially the elephant in the room, which is that, up until this point, I've shown you essentially 1 and 2 component systems, but what we've ignored is the fact that condensates typically encompass hundreds of distinct types of molecules. This has led to the classification of molecules as scaffolds versus clients, and all kinds of interesting architectures like core shell architectures. What we set about to do was to ask a question where we say that, well, a molecule that is not driving phase separation, is not required for phase separation, we'll call it a non-phase separating ligand if it can bind to the scaffold molecule that undergoes phase separation. And so the obvious question that arises is, what happens if we were to add a non-phase separating ligand to a solution of scaffold molecules that undergoes phase separation? So a cartoon might actually help us sort of understand what's going on. So if in this high resolution picture, I have a scaffold that is a triangle, a red triangle. Basically what I'm saying is that when we realize phase separation by way of equalizing the chemical potential across 2 phases, a dilute phase A, a dense phase B of the scaffold molecule, and it's the equalization of the chemical potential, which of course, as all of you know, is the partial molar free energy that controls the concentrations of our scaffold in the dilute phase A versus the dense phase B. Now, let's add a ligand, right? We'll make it blue. What do I need now? What I need, of course, is to ask the following question, which is in the presence of the ligand, what is the concentration of the scaffold in the dilute versus the dense phase? Turns out that, you know, the beauty about thermodynamics is just because you changed the underlying composition, you didn't change the thermodynamics. You essentially still maintain the equalization of chemical potentials as our constraint. And so, in fact, to ask this question of what will be the concentration of scaffold in the dilute versus the dense phase, you basically do exactly the same thing. So you say either out or the dilute phase A or in the dense phase in. Basically what you're doing is you're now equalizing the chemical potentials of scaffold, but now in the presence of ligand, okay? What this does is it says that the concentrations are now going to be set by the interactions of the ligand with the scaffold in both phases, right? You don't get to sort of just measure the affinity in the dilute phase and hope that that transfers over. What that leads to is this formalism of polyphasic linkage, which is simply the idea that given now a degree of freedom for binding, so the ligand has a choice between binding to the scaffold in the dilute phase or binding to the scaffold in the dense phase. There is no requirement that that binding has to be equivalent. And so if there is binding favorably, more favorably to the dilute phase, that's preferential binding to the dilute phase. And if there's sort of favorable binding to the scaffold in the dense phase, that's preferential binding to the dense phase. So what this leads to is the saturation concentration or a concentration of scaffold in the dilute phase in the presence of ligand, that's what all this spinach means, equals the intrinsic saturation concentration times a ratio of the binding polynomial. So what is the binding polynomial for the ligand to the macromolecule or to the scaffold in the dilute phase A versus the dense phase B? So what this says to us that in the presence of a ligand, our driving force for phase separation of the scaffold is actually going to change, right? It can only be the same if the ratio of the binding polynomials is 1. Otherwise, there is going to be a change, which is great. So now we can go back and ask the question of, given a phase diagram, and here is a system under scaffold, some particular scaffold concentration, sort of phase separating to form a coexisting dilute phase here and a dense phase here. A preferential binding to the scaffold in the dilute phase will basically now shrink the width of the two-phase regime, right? Because essentially what it's saying now is that you need more molecules to be thrown into solution in order to drive phase separation. And so basically that is quantified or pictured here in terms of the left arm of this binodal or the coexistence curve shifting to the right, meaning that we need a higher concentration. The polyphasic linkage theory is actually silent largely about what happens to the dense phase. Here we schematize this, but I'll show you that this is indeed what can happen. Conversely, if the ligand likes the scaffold more so in the dense phase, now what will happen is that you're basically stabilizing phase separation, and then in contrast to what happens here, now the blue curve basically represents the two-phase regime or two-phase boundary in the presence of the ligand, and that widens, right? So essentially, this is a very, very important point. Preferential binding means that our scaffold is exhibiting some kind of an asymmetry across the phase boundary. This can be due to the very obvious thing, which is that we have differences in concentrations of the scaffold across the phase boundary. That's a sort of duh type of point. There could be a difference in accessibilities of binding sites. There could be a difference in cooperativity of ligand binding to scaffold sites. And of course, the sort of big elephant in the room, which is we've all sort of worked on the assumption and interpreted certain results to imply that there are no conformational changes of scaffolds across phase boundaries, but this is not a done deal by any sense of the word. And in fact, it turns out that these differences in scaffold conformations across the phase boundary can enable this type of preferential binding. And by the way, I should point out that this is, I was basically a 7th grader when Wyman and Gill wrote about this. So, and I'm fairly old. So these are well-renowned concepts. I think they just bear repetition at this point. But what we're going to do is sort of go beyond the linkage theory to ask, can we uncover certain general rules of polyphasic linkage to now make things a bit more practical to help us think about how we will regulate phase separation by way of ligands, because that's the theme that's emerging. And this is the work of Kirsten Ruff, currently a research scientist in the lab, working closely with Furkan Dar, a graduate student in the lab. So what Kirsten and Furkan did was they said, well, it gets really unwieldy to start thinking about lots and lots of pen and paper theory to sort of write all these linkage relationships for fairly sophisticated scaffolds and ligands. So let's turn to LUSSI, our simulation engine that I introduced in lectures 1 and 2, where we'll basically put down sort of archetypal multivalent systems on lattices and ask what happens. So here is the model for this part of the talk. This is our scaffold. It has stickers shown as blue Pac-Men. Some stickers are connected by implicit 0 excluded volume spacers. So we're connecting back to lecture 1. And then instead of implicit spacers, a couple of the spacers are modeled explicitly as red Pac-Men. Our ligand can essentially come in different flavors, but the key point is that we could have ligands that bind to sticker sites or ligands that bind to spacer sites. And then the sticker-sticker interaction in units of sort of reduced temperature will be, let's say, -2. And then we can titrate the strength of the ligand to scaffold interactions to be sort of either half of the sticker-sticker interactions, equivalent to the sticker-sticker interactions, or stronger. Okay, so what we'll do is start to look at different types of ligands. So the first thing we'll do is look at what happens when we have monovalent ligands that interact with stickers, or monovalent ligands that interact with spacers. The gray phase boundary is in the absence of ligand, and I'm showing you here for one particular ligand concentration. And the orange phase boundary is basically what happens in the presence of ligand, right? And so when we have monovalent ligands interacting with sticker sites, depending on the strength of the interaction between the ligand and the sticker, you effectively either destabilize phase separation or basically abrogate phase separation. No big surprise here. You're competing with sites that are actually driving phase separation. The spacers, on the other hand, they also have a weakening and abolishing effect. But what they're doing here, again, remember back to lecture 1, they're adding to the effective excluded volume. And remember that our spacers enable this cooperativity of phase transitions, right? That enables the phase separation. And basically we are, by sort of increasing the effective excluded volume or effective solvation volume, we're basically destabilizing. So this will be true for monovalent ligands. Let's ask what happens with divalent ligands. So as the title basically tells you, you have divalent ligands that are going to interact with the sticker regions. And so essentially we start to see sort of a destabilization of phase separation with the divalent ligands. But the extent of the destabilization is not as pronounced as the monovalent ligands. And you're probably wondering why, because there is a cross-linking ability that's coming about from the divalent ligands, because they can actually also add to the valence. So there's a sort of, there's a destabilizing but not an abolishing effect. Now, when you have divalent or bipartite ligands that interact with spacers, or spacers and stickers, now what you actually see is the orange curves are wider than the gray curves. So you're actually seeing an increase in the driving force for phase separation. So you get this enhancement of phase separation. So let's go back and ask to what amount, right? And so basically we focused on the divalent ligands, and this is one of the central issues that comes up, which is that if I have the endogenous concentration of a scaffold that is lower than its intrinsic saturation concentration, can I have a suitable ligand or collection of ligands that can actually drive phase separation by basically lowering the threshold concentration? And the answer is yes, in that here what we're doing is plotting the concentration in the dilute phase in the presence of ligand versus the, and the ratio rather, to the intrinsic saturation concentration. If that value is 1, then the driving forces are not changing. But if that value is decreasing, we're actually increasing the driving forces for phase separation. And in fact, what you can see is that in this particular case, as you titrate ligand concentration and you have these divalent ligands that are basically interacting with the spacers, you can essentially drive the, you can increase the driving force by an order of magnitude, right? So now you have a ligand-mediated additional driver. So in other words, it's a bit sort of simplifying to say the components of condensates will either be clients or scaffolds. These ligands can actually be regulators. Now, let's go back and then ask the question that was sort of left unanswered in the polyphasic linkage formalism, which is, what do ligands do to the dense phase, right? And it will turn out that ligands will actually have a diluting effect on the concentration of scaffold in the dense phase, no matter what. So we're doing the same thing. We're measuring the concentration of scaffold in the dense phase in the presence of ligand and its ratio when compared to the absence of ligand. And I'll sort of walk you through these slides, right? So essentially divalent ligands that interact with stickers, they're destabilizing phase separation. And so what is the effect on the dense phase? We're diluting the dense phase. We seldom, these are basically statistical issues, so essentially finite size systems, but really you never see an increasing of the concentration of the scaffold in the dense phase. So even with ligands that are actually enhancing the driving forces for phase separation, what we're seeing is we're either maintaining the scaffold concentration, or rather strikingly, we're even diluting the concentration of the scaffold in the dense phase. If you stop and think about this, this makes perfect sense, right? Because essentially what you're doing is you are enhancing the driving forces for phase separation. The ligands are not just passively partitioning in, they are actually coming in and contributing to the driving force. So there has to be a make room for the regulator that's actually enabling the driving force. And so in fact, if we go back and then quantify the total concentration, not just of the scaffold, but of the ligand and scaffold, what we actually find now is that in cases where the ligand is enhancing the driving force for phase separation, you can actually see that the total concentration has gone up now, because, so essentially what happens is there's a linkage, the scaffold has made room for the ligands have come and bound to the scaffold in the dense phase for whatever reason. They have enhanced the driving force for phase separation by dropping the saturation concentration required of the scaffold, but they've also made the condensate more dense overall, right? But of course, the total concentration goes down when we have destabilizing ligands. Very cool. So now comes the, I'd say, the billion-dollar question in this field, because I'm fairly confident that one of the things that we all think to do to measure is the partition coefficients of whatever client molecules we want to measure, right? And so the question is, can I read out the stabilizing or destabilizing, i.e. regulatory effects of ligands by just measuring partition coefficients, okay? So let's define our partition coefficient. It's basically the ratio of the concentration of the ligand in the dense phase B to the concentration of the ligand in the dilute phase A. Partition coefficient greater than 1, we basically say that our ligand is accumulating more preferentially or favorably in the dense phase. If you've got macromolecular Crowders, for example, the partition coefficient will be less than 1. You'll say that it's being excluded from the dense phase. So the value of PC is something that we use a lot. What is particularly important is that it's not out of the realm of possibility that we'll find a paper where PC equals 1 is taken to mean that the ligand is essentially agnostic for the scaffold in the dense versus the dilute phase. So what Kirsten did was she visited this question and basically asked, does this have merit? And what this plot shows here is that when we consider ligands that destabilize phase separation, that means that they're basically increasing the saturation concentration. We can get partition coefficients that are all greater than 1. In fact, we can get partition coefficients that are as large as 100. Okay? This is a ligand that is ostensibly destabilizing phase separation. We can look for ligands that do not change phase separation at all, i.e. this ratio is 1. The partition coefficient is still in this gray zone somewhere between 10 and 100. So it's still accumulating, but it's not doing anything to the driving forces. And really strikingly, you can actually have ligands that, of course, promote phase separation. And this is much more intuitive, some would argue, in that you would get partition coefficients that are actually quite large, right? So what's the takeaway here? That essentially the partition coefficient has a blindfold as far as a measure is concerned in terms of telling us anything about how the molecule in question, i.e. the ligand, is affecting the driving forces for phase separation. The obvious question is why? And so Kirsten went back to linkage theory and basically was able to derive for a series of systems, but I'll show you the simplest one, the partition coefficient when we essentially use a binding polynomial that's first order across the phase boundary. It is a product of quantities. Here is the ratio of volume fractions in the dense versus the dilute phase. Here is the concentration of scaffold that's bound to ligand in the dense phase and the dilute phase. And again, that contribution from the volume fraction of the dense and the dilute phase. Put in words, the partition coefficient is not just a measure of preferential binding. It is a measure of the contributions from preferential binding and the differences of the scaffold concentration across the phase boundary. And so in effect, what's going on is that the partition coefficient really is our fairly efficient way of saying, I can tell you what the concentration in the dense phase is going to be versus the dilute phase as seen by some molecule, right? But how that molecule sees it will be sort of contingent upon two things. How is it binding and how much room is available for it, or what is the effective concentration of scaffolds, right? So what Kirsten then did was she said, well, okay, if this is true, I can solve these binding polynomial sort of equation numerically and ask to see if this is actually true, where now what we have is, let's say beta A over beta B being 10 is essentially saying that our ligand is preferentially binding to the dilute phase, it being sort of if beta B over beta A is 10, then our ligand is preferentially binding to the dense phase. If they're equal, then essentially we should see that, you know, there is no change in the saturation concentration. What happens to the partition coefficient? Two things. It's always larger than 1, and its value depends on the ligand concentration, right? So effectively what this says is that a partition coefficient in and of itself is an easy to measure quantity, but quite likely uninformative. What we will need are partition coefficients as a function of ligand concentration, but more ideally we would think measure this quantity over this quantity. So that's the takeaway. Ligands can modulate phase separation via preferential binding. I talked about what happens when you have one type of ligand, but of course you can have a whole plethora, a network of ligands. Ligands can enable phase separation at lower scaffold concentrations. So when you start thinking about endogenous levels of expression, how might I think about phase separation actually happening? Or how might I sort of ask the question of, having crossed the threshold concentration, why should I end up with a condensate that dissolves? A ligand can help do that for us, which of course means that in a cellular sense, controlling the expression levels of ligands will actually afford sort of a multitude of knobs now, because you have one scaffold, let's say, or two scaffolds or three scaffolds, but you have, let's say, n different ligands that you can start to tune, and you can start to imagine what type of combinatorial complexity a cell might have over different cellular states and fates, right? So to me, this is very exciting. So that segues, of course, to the real fly in the ointment, which is I made the very simplifying and glib assumption that we essentially had two types of molecules, a ligand that does not undergo phase separation and a scaffold that basically will undergo phase separation via homotypic interactions in their solvent-mediated homotypic interactions. But now, when you start adding other molecules into the system, you bring to bear the possibility of heterotypic interactions, which means that new rules will emerge because of the additional degrees of freedom. So I will give you sort of a current working summary of where this work stands. I should point out that this represents contributions actually from two different labs. In this particular case, non-collaborative. This is not that we have developed a feud or anything. It's just that we were pursuing this independently, which is actually kind of fun sometimes to converge upon similar findings independently. Some of you have read the paper that Josh Reback wrote recently, published in Nature. This was preceded by work that Furkan did that was published in PLOS Comp Biology. So I will talk more about our work. So we don't use the free energy formalism that Josh prefers. We prefer the formalism of slopes of tie lines because it gives us something extremely visual to be thinking about. So let's walk into this. So I'll first walk us through the problem of how to think about multi-component phase diagrams in a system where the driving forces for phase separation don't involve purely homotypic interactions. They actually, if anything, predominantly involve heterotypic interactions. And so this is the system nucleophosmin 1, studied quite beautifully over the years by Diana Mitrea and Richard Krivacki at St. Jude. And those of you who know the system know it well. It's got this oligomerization domain, these acidic tracts, and then there is a nucleic acid binding domain. The oligomerization domain drives the formation of pentamers. So essentially, this is a branched multivalent polymer that has disordered regions tethered onto a beautiful folded scaffold. It turns out that you can add arginine-rich peptides that will actually turn out to be the regulators of what's going on with nucleophosmin, so essentially the GC of the nucleolus. And when you control the flux of arginine-rich peptides, you essentially either enhance the stability or weaken the stability by a form of complex coacervation. It's not purely electrostatic in nature because, as we've discussed, arginines versus lysines and aromatics, etc., bring lots of interesting things to the party. So what Richard's lab has done over the years, driven primarily by Diana, is to demonstrate that you can come up with a sort of parsimonious version of nucleophosmin that essentially has the pentameric core and the acidic tracts, and then you can study the phase behavior as you titrate the concentration of arginine-rich peptides, where what you do is you control the valence of arginines, i.e. the number of arginines, or let's say even the patterning of arginines. So make a super sticker of arginines connected by a flexible linker to another super sticker, right? Which is exactly what this is. So Furkan basically visited the problem of calculating phase diagrams, and I'll use this system to first walk us through sort of some topological features of phase diagrams in multi-component systems that have begun to be appreciated by us, by Cliff's lab. Richard has sort of always known this. Mike, I think, always knew this, Mike Rosen. And more recently, Sam Safran and Emmanuel Levy's lab have done some beautiful work in this area, and so has Priya Banerjee. So let's look at, our sort of physicist's version of N130 and RPL5. Basically, this is telling us that we have a sort of divalent molecule, so we flood our system with sort of multiple RPL5s. We then, essentially can titrate the concentration of N130. Note these curious units because we're doing simulations on a lattice. So our concentrations are measured in units that are per voxel of the lattice. There's no micromolarity here, right? And then we've got RPL5 that is titrated here. So I'll walk you through some important features. First and foremost, the purple contour essentially is now our phase boundary or coexistence curve. It's not a binodal because, of course, what we have are the possibility of, higher number of nodes, if you will. We can also calculate the percolation line as discussed in the first lecture and basically ask, what fraction of the concentration sort of envelope essentially what would be a networked droplet, and that would be the green contour. And then, of course, you have the bulk gel that is forming out here. And let's walk us through some features of this. So let's now say something like this. We'll keep the concentration of N130 fixed and basically increase the concentration of RPL5. So we'll go through the two-phase regime. That means for all points that lie between the purple boundary, we'll end up with phase separation where basically we'll get two coexisting phase corresponding to sort of this value here and this value here. But importantly, and similarly, we'll have the same thing if we keep RPL5. But one of the things that you will see, of course, is that this closed loop behavior enables something called reentrant phase transitions, right? So essentially, by controlling the concentration of the second molecule that's driving phase separation or required for driving phase separation, you can essentially cause these molecules to exit the two-phase regime, right? And so Priya Banerjee, when he was a postdoc in Ashok Dennis's lab, first introduced this idea to our literature. It's been sort of prevalent in the phase separation literature for some time. But then there's also something that Tyler Harmon sort of discovered and Furkan Dar sort of rediscovered, which is the idea that the percolation line or percolation boundary is going to have this parabolic shape, also exhibiting a form of reentrant behavior, mainly because essentially what will happen is that above here we have sort of too many N130 molecules. Basically, you cannot really network. Here you have too many RPL5 molecules you cannot network. So you essentially get these reentrant features, both for phase separation as well as percolation. Okay, so what we'll do is sort of go back and now start to think about some model two-component systems. So Furkan designed this, where we'll say that we have got sort of two systems that require one another to undergo phase separation. So the only way they can undergo phase separation is via heterotypic interactions. Here's the interaction table. We can have that system to which we add a client, which following Mike Rosen's sort of schematization will essentially be a reduced valence version of polymer 1. We'll now say we'll add some homotypic interactions. So now you start to see interactions showing up on the along the diagonal. And so our blue molecules can interact with themselves. And then the final scenario is we say we have only homotypic interactions, but then we have a Crowder, right? So essentially the only thing that the black polymer here is going to do is serve to contribute excluded volume effects. And so we ask, what do these phase diagrams actually look like? So in the next few slides, there will be two sort of scales that I'll be using. I'll be using the linear scale here because that helps us highlight the dense phase arm. And then I'll show the logarithmic scale because that helps us highlight the dilute phase arm, which basically otherwise makes the phase diagram look like a guitar pick because you don't really have the concentration resolution down here. It still has this closed loop nature. And so essentially what happens here is with heterotypic interactions, you get a beautiful, perfect closed loop. And it's essentially symmetric about the 1-to-1 ratio, right? Add a client. And since the client interacts with the red polymer and you start to increase the asymmetry because now, in fact, there is a sort of bulge that is forming in our phase diagram. If you add homotypic interactions, by the way, the temperature is fixed here, you essentially now start to fundamentally change the shape of the phase diagram. That closed loopness is gone. And in fact, you start to see sort of more of a verticality here. So it's becoming less sensitive to the red polymer, so to speak. And really, basically, you're getting the sort of phase boundary that looks more like what we've come to expect with binodals as a function of temperature. and the really, really oddball, which is what happens in the presence of a Crowder. Essentially, these are depletion-mediated attractions, and so essentially what you say is you get what looks like, sort of two lobes of a boomerang of some sort, but basically this is the dilute phase, this is the dense phase, and we'll get to what is going on with the Crowders. Now, these types of phase diagrams will have tie lines, they have slopes, that they have implications for thresholding behavior. This will sound like a mouthful. In the few minutes that I've left, I'll explain what I mean here. Let's go back to the phase diagrams we know and love. Concentration on the x-axis, temperature on the y-axis. The two coexisting phases, let's say I have my system is at this particular concentration, it separates into these two coexisting phases, gray and green. And there is a tie line that passes through this black point and joins the two coexisting phases. That basically is the line that connects the 2 points that are of equal chemical potential, right? The tie line is horizontal. What is the ordinate here? It's temperature. That is basically saying that the temperature in the dilute phase and in the dense phase are exactly the same, right? So as a consequence, but that's going to be different here because in our multi-dimensional or multi-component systems, now our tie lines actually have slopes. So in the previous case, the tie line basically was horizontal, zero slope. Here we're basically going to have, some finite slope. And also what's interesting is that if you convert this from linear space to logarithmic space, essentially our tie lines actually start to have curvature on them. So not only do we have to recognize that when we go to multi-component systems, tie lines are not horizontal, we have to recognize that we have to worry about, are we plotting our phase boundaries in linear versus logarithmic space in order to figure out what sort of tie lines are we working on. So what are the implications of having non-zero slopes? So the canonical expectation is, let's say I were to titrate the concentration of a scaffold molecule that's driving phase separation. I measured the amount that remains in the dilute phase or in the solution. I'll come to some threshold concentration, and then that will plateau, right? That's our saturation concentration. This is basically the way we think about the problem. But that goes out the window now. So essentially what I've done here is basically said, I'm going to fix the concentration of B, vary A, so that means, that's right, so we're moving up along the ordinate, and we're going to measure how much of A remains in solution. So basically we hit the phase boundary when we sort of come to this point here. You actually see some completely non-trivial behavior. And then, of course, when we exit the phase boundary, we catch up back with the dashed line, right? And this is shown in logarithmic scale, which is important. So the key point is that the concentration in solution of molecule A does not saturate, but it's set by the slope of the tie lines, right? So let's return now to our sort of model systems and actually see what sort of behavior we get. So essentially what we'll find is that the slopes of the tie lines will sort of approach zero, and therefore we'll start to see this leveling off behavior only when we add homotypic interactions. But if we have purely heterotypic interactions, we're basically going to see variable concentrations in the dilute phase as we change the total concentration of a particular molecule. So here are the tie lines. Again, the bottom part here is showing what happens in linear scale, here what happens in logarithmic scale. And you can actually start to see how these slopes start to shift. They become completely funky when you start to add Crowder. And let's go back and look at what happens to the concentration of component 1, let's say our blue polymer, in the dilute phase as we titrate the total concentration here. And this would be of component 2. I'll basically look at sort of this system here. Notice you never really get any kind of saturating behavior, but instead you start to get this dipping type of behavior. So in other words, it's not that the concentration will saturate at some value, it will go below some threshold, and that the value that it falls below will be governed by the strength of the heterotypic interactions. But what's really fascinating is that in the case of the Crowder, you don't get leveling off behavior either. So in fact, what's going on, is the amount of our scaffold molecule that remains in the dilute phase actually starts to go down. And that's because the Crowder is now taking, it doesn't want to go into the condensate, it's taking up more and more of the dilute phase, right? And so basically what this says is that it is really a tricky issue to basically say that, you know, hey, I can unmask the contributions of homotypic interactions by adding Crowders, because the underlying physics actually changes when you start to add Crowders, because you're driving phase separation primarily via depletion-mediated interactions. Now, of course, if you're convinced that in the cellular milieu, there are bona fide excluded volume-based Crowders, these experiments will have some merit. But I think if the intent is to unmask the contribution of the homotypic interactions, proceed with caution. Okay, so I will stop there. Suffice it to say that we're just starting to sort of, you know, it's the tip of the iceberg here. There's a heck of a lot more to understand regarding this complex interplay between spontaneous and driven phase transitions in multi-component systems. There are going to be some very interesting regulators. Ligands I talked about, post-translational modifications, post-transcriptional changes are also going to be super important. And thinking about now heterotypic interactions and the complexities of multi-component systems will be absolutely imperative. Let me stop there. Let me thank the people who've done the work today. I mostly talked about work that Steve Boynams did on the protein RNA side in collaboration with Alex Holhouse. And then the latter two stories were driven exclusively by Kirsten and by Furkan. And thank you for your time and attention.
Thank you, Rohit. Again, just as in the last 2 weeks, spectacular lecture, lots to chew on, lots of great results to think about. We have a number of questions that have come in, and I know that we're at the top of the hour, so we don't have too much time, but why don't we jump to Charlotte. Charlotte had a very interesting question about post-translational modifications.
Hi, yeah, can you hear me?
Yes, Charlotte.
Hi, so I guess you sort of alluded to it on that final slide, but I was wondering if when you discussed how ligands can affect the percolation concentration or saturation concentration of one component in a multi-component condensate, how might one think about post-translational modifications on that same protein modifying the unmodified partners in the condensate?
Yeah, so you can start to see, right? I mean, that there is now going to be quite a bit of an interesting sort of complexity emerging. So let's start simply with, I've got ligands, I've got post-translational modifications to think about, or post-transcriptional if I have RNA. And then I've got our molecules that are driving phase separation either by homotypic or heterotypic interactions. So we've got basically at a minimum sort of 3 players that we've got to think about, right? Now, of course, I can, there may not be just one ligand, there may not be just one pair of heterotypic interactions, but the question is, are these rules extractable? And the answer is absolutely yes. And so a lot of the sort of intricate phase behavior that I think we've come to know and appreciate in the context of condensates is going to sort of become manifest, and that will give rise to, for example, the ability to fluidize certain components, the ability to realize wetting versus de-wetting behavior, the ability to get unmixed condensates, the ability to, let's say, use ligands that preferentially interact with, let's say, one component of the scaffold, and let's say there are other scaffolds that can engage in homotypic interactions. You can actually sort of dissolve certain, do selective dissolution of condensates, right? Which is actually going to be really interesting, and I rather suspect quite important for biology. So I guess the short answer is yes. The long answer is that there's going to be a lot more interesting stuff that's going to come along. And the real challenge, I think, here is going to be how we sort of formalize this in terms of both the theory side and also in terms of connecting these to measurements, because fundamentally, how do you measure, the challenge is how do you measure the concentrations of more than a pair of species, right? I mean, that would be the sort of, to me, the billion-dollar challenge, right?
Thank you.
That's great discussion. I think Abid, you had a very interesting question about what can be learned from the simulations about some of the subtleties of these systems.
So Rohit, with respect to Stephen and Alex's work, can you predict from the simulation that the length of the DPRs will require an elevated amount of energy to overcome this barrier between a dynamically arrested sort of metastable state and the ultimate spherical state? And I ask this question from the perspective of someone who's, you know, tangentially working in neurodegeneration. And we tend to think of aggregates as an endpoint emerging from a liquid thing.
Right.
But what this work suggests is that it might an amorphous thing, an aberrant phase transition, might actually be something on pathway to a condensate, and energy in the cellular sense isn't heat, but rather helicases and chaperones. And so might we be looking at an endpoint that is really not emerging from a droplet, but rather arrested on the way there?
So I have to first do this, because I think I got through. So you're absolutely right, Pete. And so the issue that arises, right, is that there are two polymers whose length affects one can start to titrate. And of course, the way to do that would be to titrate the length whilst keeping track of what that's doing to the sticker valence. So for example, if I start to dope in predominantly purine-rich regions, some pyrimidine-rich spacers, for example, I have increased the length, but I've perhaps not created as much of a problem for entanglements and therefore for the dynamical arrest. Likewise, the experiment that we're actually setting up to do and think about computationally as well as experimentally is not just think about PR repeats, but then start to dope in, you know, the occasional lysine, for example. And I should point out here, throw a shout out to Suam Wong and TJ Ha at Hopkins. They have a work that I think will see the light of day soon. And I think she's talked about this, so I'm not sort of disclosing privileged information because it's on bioRxiv as well, because it turns out that she can interpret the effects of particular arginine to X mutation or a glycine to glutamate mutation in FOS as being due to dynamical arrest, right? Because you can actually demonstrate that given enough time, in this particular case, they didn't go after the particular question that you asked, but this is precisely the point. I think helicases, energy-driven processes might well be there to enable the traversing of these barriers, right? So you're absolutely right. We shouldn't think about, you know, the minute you start to see irregularly shaped condensates, we shouldn't think that these are solids that came out of liquids as crucibles. They could very well be dynamically arrested phases.
I think that's a really interesting mental model to think about some more. I love that. We have a question also from Alan, who also wondered about how the dynamic properties of proteins affects the behavior of condensates. Alan.
Yeah, so beautiful talks have been tremendously helpful. I'm just curious, as you actually push to these really high partition coefficients where the protein is effectively only within the condensate, what happens to the dynamic properties within the condensate and exchanging between the dilute and the dense phase?
Yeah, so one of the missing pieces of the puzzle here that I didn't write on is the dynamics actually becomes really, 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 really important, right? Because and so one way to step back and think about this is, I think if we connect back to lecture one, the first point I would make is that we need to stop thinking about these as purely viscous bodies. These are always viscoelastic, which means that the viscosity and the elasticity are time dependent, right? And that will mean that as we change both spatial inhomogeneities or local densities inside condensates, we are likely to start seeing time-dependent conversions between viscous and elastic properties. And just to put this in context, I didn't show this, but in the experiments that Stephen did with the protein RNA mixtures, there was actually a beautiful coexistence, dynamically speaking, whereby from a FRAP standpoint, if you all you did was to take the fluorescently labeled RNA and did a FRAP analysis on that, you would conclude that these were solid-like condensates. But if you, in the second channel, because you have two different constructs that are labeled, the protein and the RNA, but when you look at the FRAP and the timescales for recovery of the fluorescence, when you look at the protein side, it essentially looks like what we've become accustomed to looking at, right? And so there again, there appears to be, and that gap between the recovery times of the protein and the RNA are again very dependent on the sticker types on the protein and the RNA. So going to your question, I think what we're going to start seeing is possibly, we've been talking about thermodynamic coexistence of phases, but I think we're probably heading toward also thinking about the dynamical the coexistence of dynamical phases inside of condensates, which will therefore give rise to a really rich sort of spectrum of timescales, but a time dependence to those properties as well.
That's great, great answer. Okay, I think we're running a bit late, so I think maybe we'll just we'll call it here. Rohit, again, everyone on the call, everyone who's come to all three lectures really wants to thank you for all the effort you put into these lectures and how brilliantly you delivered them. So thank you very, very much for all of the hard work.
I should say this was inspired by Rebecca Sparks, who has not actually revealed herself on here. At least I haven't seen her. I know she's there somewhere. But Rebecca, you were the one who sort of prompted me to do this. I'm truly appreciative. And Jill, you've basically held me by my finger as I've gone through this. So thank you so much. And thank you, Mark, for your support. This has been loads of fun putting it together. And, I'm happy to, and I should point out one last thing, which is I do have, I think something like 27 questions from the last time. So yes. I collected all of them. What I decided to do was to see what new questions came up. And then basically I will be super proactive to make sure that before Jill uploads this last lecture, you get the answers to all questions that came from lectures 1, 2, and 3.
That'll be wonderful. That'll help everyone. So thanks again for that too. All right. So I think we'll sign off at this point.
Yeah.
All right. Thank you all. Thank you, Rohit.
Thank you, Mark.
Okay. Take care. Bye-bye, everybody.